All right, here we see in the first question, they have asked us to find out which charge value is physically not possible. So we know that the minimum charge is the charge of an electron, which is basically 1.6 into 10 power minus 19 coulombs. So whatever charge we may have in the universe, that will be a multiple of this value, right? So clearly from the options you see that option number C is not possible because this is lower than the minimum existent possible charge in the universe. And all the other values you see will be a integer multiple times of this incremental charge, electronic charge. Now for question number 2, part 2, we see that we have to find the equipotential lines for the charges plus Q and the minus Q. So this is the plus Q charge, right? And this is the minus Q charge. And now the curved lines are the electric field lines. Now you have to find out the equipotential lines because of this electric field distribution. Now we know that electric field is minus dB by dL. This is which basically means that electric field is a derivative of the potential function, right? That means the electric field lines have to be perpendicular to the equipotential surfaces, right? Or the equipotential lines. Now from here you have to look for the options A to E such that the electric field lines are perpendicular to these options. Now, if you see option number A, you see at all points for this line at all points, right? For all points at this line, along this line, the electric field lines are not perpendicular, right? If this was supposed to be a equipotential line, the lines are not perpendicular. You see this angle is not 90 degree, right? So as this angle is not 90 degree. So A cannot be an option. Similarly, E cannot be an option, D cannot be an option. For C, you see the electric field lines and the equipotential lines are not perpendicular, but they are parallel, right? So therefore, C cannot be an option also. Now for line number B, you see that the equipotential lines, right? At this, it's along the origin of this dipole, right? Through the center of these two charges. Now here you see at these points, the electric field lines are always perpendicular, right, to this line. So you see that only option number B can be your equipotential lines. Now for part 3, you see there are two positive charges, right? Plus Q1 and plus Q2. And this is your third charge, which is the summation of Q1 plus Q2. Since these two charges are positive, therefore this charge also have to be positive. Now they have asked you to find if, like, in which condition the electrostatic forces will balance out the gravitational force, right? But since you see these electric forces are repelling, right? Because all are positive charges, therefore you can never balance out the, let's say, downward gravitational force with an upward electrostatic force, right? Because for an upward electrostatic force, you need this to be maybe at least negatively charged particle, so that there will be an upward attractive force to balance out this downward gravitational force. Since all are positive charges, there will be a repelling force, therefore the balance cannot be possible. Therefore, option D is your correct option. Now in part 4, you're asked to find out the formula for the system of cylinder capacitance, right? So this is one cylinder, this is another cylinder, the dimensions are given, the length is given. Now this is just plain straightforward from the theory that we have seen in the class, that your option D is the correct option, which basically defines the capacitance of such a cylindrical conductor system. Now continuing from there, we saw that our capacitance equation was basically 2 pi epsilon naught length by natural logarithm of b by a. Now they have asked you to find that if my length is increased 7 times, then the original value, what should be the ratio of the radiuses of the cylinders, right? So now let's say if I increase this 7 times, right? If I increase this 7 times, so therefore to cancel this 7 times, I also need a 7 at bottom, right? So therefore my logarithm of the new, let's say, radius ratios also have to be 7 times the original radius ratios, right? Such that my 7 from the denominator cancels out the 7 from the numerator, such that my overall formula remains same. So therefore for this to happen, you see, for this to happen, I need is I have to start from 7 of logarithm natural log of b by a, right? So therefore you can take this 7 into the power, right? Since it's a logarithm function, so therefore it becomes b by a power 7, right? Therefore you see that our option number E is the correct option. Now in part 6, we are asked to find out for spherical conductors. So basically these are two spherical conductors with radiuses a and b, to find out the capacitance of such a spherical conducting capacitance, right? The system of the capacitance of this spherical conductor system. And we know from theory that our formula is given by option number B. Now for part number 7, you have asked to find out the ratio of the energy stored in the system of a two spherical system compared to a system where you have a single spherical conductor, right? So we know that our capacitance formula for a spherical conductor system is given by 4 pi epsilon naught A times B, right? Divided by B minus A. Now for a single spherical conductor system, I'll assume that my B is moved to infinity, such that this moves away far from the inner conductor A, such that it becomes a single conductor system. So therefore I take my B out as a common from the denominator, right? So this becomes A by B, right? So therefore I end up having a capacitance of, I can write this formula, right? Now if my B moves to infinity, right? If it moves to infinity, and if I plug this value into this equation, I see my capacitance of the system for a single conductor is just 4 pi epsilon naught A, right? So this is the formula that I'll be comparing with two conductor system. This is for two conductor system, right? And this is for one conductor system. So I'll be comparing these two formulas. So now if you just take the ratio of these two formulas, right? See, in this case, if I take u infinity by u, right? That's just 4 pi epsilon naught A. And this one is for the two conducting system, right? For the two conducting system, this is 4 pi epsilon naught A. I'll use this one, right? So you see, I end up getting 1 minus A by B ratio, right? So for this system, the ratio of the energies would be A minus 1 minus A by B. So therefore, my option number A is correct. Now they have asked you to do U by U infinity, right? But it seems the ratio would be just a reciprocal of this one. So therefore, you can choose this option because this can be just a typo mistake. All right. So in question number 2, we see that we have been given a magnetic field and a loop of wire is also given with a resistance 10 ohms through that magnetic field, right? And the magnetic field direction is into the page, as mentioned. It's into the page, right? And it's decreasing at a rate of 1.5 times 10 to the power 2 Tesla per second. Therefore, you know that your D is decreasing, right? So that's a hint that's given because it will determine the direction of the induced current, let's say, from Lenz's law, such that the induced current will try to increase the reduced magnetic field. Now, you are asked to find out the reading on the ammeter, right? Now, in this case, you see that you have a decreasing magnetic field. Now for this case, actually, if you have a voltage given, right? If you see you have a voltage given, now you would assume that my current in the circuit will be just V by R, right? It would be just, let's say, 5 by 10, and it will be just 0.5 ampere, right? But it's not the case because of this decreasing magnetic field, there will be also an induced current which will be trying to change this current because of the voltage source, right? So we have to find out the induced EMF in this case. Now, because of this voltage source, we would have 0.5 ampere, right? But that's just half of the case. So let's find out what's the induced EMF in this case. So we know that from Faraday's law, the induced EMF is d phi v by dt, and we know this one as a hint because it's given, the change is given, which is 1.5 into 10 to the power 2, right? And since it's a single loop wire, so your n is equal to 1. Now, so we end up getting d phi b by dt, right? But what's our phi b, right? What's our phi b? It's b times a, right? And what's our b? We know that this b, this changing rate b, right? So area is fixed. The area is the area of the loop, which is 10 centimeter times 10 centimeter, right? So that's like, if I convert it to meter, it's like 0.1 squared, right? Now, our b is a function of time, right? Because it's changing at a rate. So our d phi by dt is just basically equal to dB by dt times area, right? So we know the area is 0.1 squared in meter, right? And we know our dB by dt, which is 1.5 meters per 2. So therefore, our induced EMF is just dB by dt times area, which is 1.5 into 10 to the power 2, right, per second times 0.1 squared. So therefore, our induced EMF is 1.5 volts, right? So this is 1.5 volts. Now you see what should be the direction of the induced current, right? Since the magnetic field is into the page and it's decreasing, therefore the induced current would be such that to increase this magnetic field, right, which is also into the page. So therefore, if we apply the right-hand grip rule, thumb pointing to the direction of the magnetic field, so therefore you see there should be an induced current in this direction, right, which is opposite to the current because of the voltage source, right? So therefore our induced current, right, I call this induced current, What's the amount of it? It's 1.5 divided by 10, which is 0.15 ampere, right? So therefore, what is our net current through the ammeter? Our net current is I minus I induced, right? Which is just basically 0.5 minus 0.15, which turns out to be 0.35 ampere. So therefore, our ammeter will give you a reading of 0.35 ampere. So which is option number B. Now in part 2, you see there are two straight wires, right? Straight portion wire carrying currents, and also there's a part of the circular section. Now you're asked to find out the magnitude of the magnetic field at point P. Now the only contribution of the magnetic field that's being generated by a current flowing through this conductor is because of this circular region, right? And if we use our right hand grip rule, thumb pointing to the direction of the current, we see that our magnetic field will be curling up such that we have a magnetic field like this, right? We have such yes, we have such a magnetic field. All right. Now the only contribution we have is from the circular loop. So we know that for a circular loop of wire, for a part, if a current I is flowing, we know the magnetic field is given by mu naught I theta by 4 pi r, right? In this case, your r is the radius. So in this case, your r is basically r. And what's your theta? Your theta is pi by 2. Right? So now once you plug in the values, you will end up getting B is equal to mu naught I by 8 R, right? So which is your option number D. Now for part 3, we see that they are asked like there is a charged particle at rest, right? So it's not moving in a magnetic field which is suddenly turned on. So basically you have a magnetic field, let's say B, and the magnetic field points to the z-axis direction, right? Now, what is the direction of the net force acting on the charged particle? Now, remember, for a charged particle moving inside the magnetic field, there will be a force, right, given by QV cross B, right? Remember? So if there was a, let's say, magnetic field, and if there's a charge moving inside the magnetic field with a velocity v, right? So therefore, depending on the charged particles polarity, positive or negative, it can move upwards or downwards, right? But the idea is like the charge needs to have a velocity, moving charge inside the magnetic field. Since the charge is at rest, there is no net force acting on the particle. So therefore, option number E is your correct option. Now in part 4, you see that they have asked you to find out the induced EMF across the wingtips of an airplane of a wingspan of 64.67 meters when it's traveling at a velocity of 913 kilometers per hour, right? And with through the magnetic field, the Earth's magnetic field is 5 times 10 to the power minus 4 Tesla, acting downwards, right? Now you have to find out the induced EMF magnitude. So now when we know from Faraday's law, it's minus n d phi b by dt, right? Now, since it's a single wingspan, so we can consider this to be a single while loop problem. So we can consider n to be 1 in this case, right? So this basically turns out to be d phi b by dt, right? Now, what's our phi b? Our phi b is v times area, right? Now our B is fixed for our magnetic field. The Earth's magnetic field is fixed, but the area is changing because like if we consider the wingspan length, right? Let's consider this is the airplane wing of length L, and it's moving at a velocity v, right? It's moving at a velocity v. So per second, it's covering this much area, right? So you see your area is now a function of time, right? So therefore, in this case, this will be b times, you can say, dA by dt, right? So dA by dt basically means just L times velocity, right? Because this length is changing with time, which is, if I call this L2, right? L2 is changing with time, so therefore my dL2 by dt is just the velocity, right? So that's why it's just length time velocity, which is the area. Now you have all the values. Now if you plug in these values, you'll get an induced EMF of around 8.2 volts. Now remember to convert the velocity, which is given in 913 kilometer per hour, to meter per second. So after you convert, you'll get 253.61 meter per second. So once you plug this value into this equation, you'll get that induced EMF is 8.2 volts. So option number A is the correct option. Now for part number 5 is given that you have a steady state current. So basically you have a DC current flowing through a long straight wire, right? So you have a steady current, let's say this is a wire, and the current I is flowing through it. Now this will have a magnetic field. The direction of the magnetic field will be given by right hand grip rule, and what they have asked you, like a sphere of radius r is placed near it, right? So I can consider a sphere of radius r, right? So I can consider this is a sphere of radius r, is placed near it, and now you have to find out the total flux passing through the sphere. Now the sphere is a three-dimensional thing, right? But since this flux, this magnetic, let's say this magnetic field will be generated like this, right? Will be generated like this. So therefore, the amount of flux going through the sphere is just basically its two-dimensional cross-sectional area, right? So therefore, for phi b is just b dot a, right? So our area is just, you can say, it's just pi times r squared, right? You can consider this is a two-dimensional area, but problem is this magnetic field, right? It's changing with radius, right? Because we know that for a long wire with a current I flowing, our magnetic field is given by mu naught, right? Divided by 2 pi r. So this is a function of radius and it's changing with distances. And they said the problem said that the sphere is placed near to the wire, so depending on how much distance, how far it is placed, the b would change, right? So therefore I would need more information to calculate. So therefore I would say that option E is the correct answer. Now we move to circuit. So you see this is question number 3, and they have asked you to find out the current I naught using mesh analysis, right? So now we see that clearly we have 3 loops here. So I can consider this to be my loop 1. So I consider this is I1, this one is I2, and this one is I3, right? So now I know that from here I already know that my I1 is equal to 1 milliamperes, right? Because the direction is matching with the direction of the current source, so I know my I1 equal to 1 milliampere. So now you have 2 unknown currents in the 2 loops, I2 and I3. So basically you need 2 equations to solve this, right? So therefore, if I do write the equation for I2, so I assume my I2 is greater than I1 and I3. So therefore I'll write the equation for loop number 2, which is basically equal to 4k I2 minus I1 minus 2 plus 2k I2 plus 4k I2 minus I3, right, equal to 0. Now, why I considered 4k? Because I have 2k I2 minus I3, I have another 2k I2 minus I3, so I can just combine them together to form 4k I2 minus I3, right? So once I simplify the equation, I get, and I'll instead of I1, I'll just plug in the I1 value, which I know, right? So once I do that, I get 5k I2 minus 2k I3 is equal to 3. So this is my equation number 1, right? Now for loop 3, I assume that my current I3 is greater than I2 and I1. So considering that one, when I write my loop 3 equations, I end up getting I3 minus 4k I3 minus I2 plus 2k I3 is equal to 0. So once I simplify, I get minus 2k I2 plus 3k I3 is equal to 0. So this is my second equation, right? So once I solve these two equations, two variable two equations, I end up getting my I2 to be 0.82 milliamperes, right? And my I3 to be 0.54 milliamperes. Now, what's my I naught? According to the convention, you see, according to the convention, this is my I2, right? And this is my I3. So what's my I naught? My I naught is just basically I2 minus I3, right? So which is just 0.28 milliamperes. Now for the part B, they have asked us to find out the current in the 4 kilo ohms resistance, right, which is this one, and the power absorbed by this resistor. So that means I don't need, now if I want to find out the current through the 4k ohms resistance, right? So I can, I know that from my mesh analysis, right? From my mesh analysis, I know my I1, I2, and I3, right? So what's my, I'll just repeat the values here. Okay, now what's the current through the 4k resistance, right? So I can term this as Ix, and I knew from my mesh analysis convention, this is my I1 and this is my I2, right? So what's my Ix? My Ix is I1 minus I2, right? So which is basically 0.18 milliamperes, right? So I know my current has to be 0.18 milliamperes, but you have to use superposition, right? So since I am using superposition, you see I don't need this part of the circuit, right? Because if I use superposition, then I have to go do mesh again and again. So what I will do is, like, I will simplify this part of the circuit, right, to find the equivalent resistance. So you see, for that to happen, I have these 2 kilo ohms in series, right, and these two 1 kilo ohms in series. These two are in parallel, which is also in series with these 2 kilo ohms, right? So basically, I can write an equivalent circuit. I can draw an equivalent circuit like this, right? So that I reduce the number of nodes and the number of loops. So if I apply mesh or nodal, I have to solve for less equations, right? So now what's my this resistance? This resistance is just basically 2 kilo ohms, but these two kilo ohms in series, right? So which is 4 kilo ohms in parallel with these 2 kilo ohms, 1 kilo ohms in series, which is 2 kilo ohms. So this 4 kilo ohms is in parallel with this 2 kilo ohms, right? And this entire thing is in series with the other 2 kilo ohms, right? These 2 kilo ohms. So my net resistance is just 3.33 kilo ohms. So I'll just write this 3.33 kilo ohms, right? So now you see this one is easy for me to consider. Now, if I want to find Ix, right? If I want to find Ix using superposition, so I can consider two circuits, right? So you have to consider for each independent source, you have to consider one circuit. So since there are two independent sources, one for the current and one for the voltage, you have to consider two circuits. If there is a dependent source, do not consider another circuit for the dependent source, because the dependent source cannot supply power on itself. Now, I can consider the contribution of my current source only. For that, I will turn off my voltage source. So that means my voltage source basically becomes a short circuit, right? So I'll call the contribution of 1 milliamperes to be Ix prime, right? So you see this 1 milliampere will be divided up into these two branches, right? So basically I will have to apply a current divider, right? I will have to apply a current divider. So what's my Ix prime? So if I apply my current divider, my Ix prime is 3.33 kilo divided by 4k plus 3.33 kilo ohms into 1 milliamps, right? So my Ix prime is just gonna be equal to 0.45 milliamperes, right? And then I will have another circuit which is basically giving me the contribution of the voltage source only. So for that one, I will turn off my current source. That means I replace that by a open circuit. So when I do that, I'll get a circuit like this. So I'll term this current to be Ix double prime, which is the contribution of this voltage source only. So you see there will be no current going in this direction, right? Because it's an open circuit, so I can just ignore this 1 kilo ohms. So and this is a series circuit of with 4K and 3.33K in series, right? But you see this voltage source is supplying current opposite to the direction that I'm interested in, right? The Ix. So therefore my Ix double prime in this case will be negative because the direction is opposite, and the amount will be just the 2 volts divided by 4k plus 3.33k, right? Which should be equal to minus 0.27 milliamps, right? So now what's my Ix is the contribution of the current source only plus contribution of the voltage source only. So which should be equal to 0.45 milliamps minus 0.27 milliamps, which should be equal to 0.18 milliamps, which I already know is going to be the right answer, right? Okay. So now once I know my Ix, so what's my power absorbed? My power absorbed is just Ix squared, right? Times the resistance. The resistance is 4 kilo ohms, right? Which is basically IR squared. So I square R, right? So my power absorbed is 0.13 0.13 milliwatts. All right. Now this is question number 4, part A, right? So this is your question. Question number 4, part A. This is Q4. Now here you see that there are two independent sources, one current on one voltage, and there is a dependent current controlled voltage source, right? Now they have asked you to find the Norton equivalent to the left of the nodes CD, right? So you have to consider only the left portion of the circuit, ignore the right portion right now. So now you have to find out the Norton equivalent, right? So we know that the Norton equivalent is just basically would be something like a current source, right, with a resistance in parallel, which you can also combine to do source transformation and find out the Thevenin equivalent, right? With the RThevenin to be equal to Rn, and the VThevenin will be IN times Rn. So now you'll be looking for a circuit like this one. This is your C and D terminals, and the right-hand circuit will be the same as before, right? So you want to replace the left-hand circuit with a current source at the resistance in parallel. Now, for that to do, what you can do is, first of all, you just consider the left-hand circuit only, right? So I just consider this to be 4 milliamps, 4 kilo ohms, right? This is 4 kilo ohms, right? And this is 8 kilo ohms, and this is 16 volts, and I do a short circuit across the CD terminals, right? For Thevenin, I keep it open, but for Norton, I will have to short circuit it, right? So once you short circuit it, you see the current because of this 16 volts, right? The currents because of this 16 volts will be flowing only into this circuit because there is a short circuit across it, right? There will be no contribution to the left-hand circuit because of this 16 volts. Similarly, for this 4 milliamperes, the current will be split up into this direction, right? And through this 4 kilo ohms. And then it will just continue with this short circuit and come back to the source. It will not enter into this 8 kilo ohms branch. So basically you have a current divider, you see, and a series circuit with 8 kilo ohms in series with 16 volts, right? So now what's your Norton current? If I consider this Norton current, so your Norton current would be a current divider. So since both the resistance of the parallel branches are same, so therefore the current will be split up into half basically, right? So this is 4 milliamps plus, because of the voltage source. So the current because of the voltage source is 16 divided by 8 kilo ohms, right? So this is just basically your 2 milliamps plus 2 milliamps, which is basically equal to 4 milliamps. So that's your Norton current, right? So that's 4 milliamps. Now, what's your Norton resistance? Now, for Norton resistance, you keep it open, you turn off all the independent sources, current source will be open, voltage source will be short. If there is a dependent source, you have to plug in another 1 volt source or 1 ampere current to find out the RThevenin or R Nortons. Since in this case I don't have a dependent source on the left hand side of the circuit, so I can just ignore adding that up. So I'll just turn off all the sources. So my current source is off, so I just ignore that one. Then I'll have this 4 kilo ohms and this 4 kilo ohms in series, and because the voltage source is turned off, it's short circuited, I'll have 8K parallel, right? So I'll have a circuit like this one. So what's my R Norton? You see my R Norton is just 8 kilo ohms parallel with 4 kilo ohms plus 4 kilo ohms, which is also 8 kilo ohms, right? So therefore my R Norton is just basically half of that one, which is just basically equal to 4 kilo ohms, right? So my R Norton is also 4 kilo ohms. So this is the Norton equivalent circuit that they have asked us to find. Now, for the next part, they have said find the Thevenin equivalent between nodes A and B using the results from A. So from the part A, it's like you have to assume the left hand equivalent to a Norton. So I replace the left hand circuit with a Norton equivalent that we have just calculated, right? With the current source and the resistance in parallel. Now you have to find out the Thevenin equivalent. Now, for that to happen, first of all, I have to find out the voltage, Thevenin voltage across the open terminal, right? Across this terminal, Thevenin voltage. Now you see, since this terminal is open, the current through the 3 kilo ohms is 0 because no current can flow in the open circuit. Therefore, the voltage drop across it is 0. So my Thevenin voltage is basically the voltage across this 1 kilo ohms. Right. Now, since I know this current source current, I could apply a mesh analysis, right? So that will just give me to solve for only one loop. So I can just use mesh analysis in this case. So once I do the mesh analysis, I know my I1 is 4 milliamps, right? And if I do write the mesh current for I loop 2, assuming I2 is greater than I1, so I get this equation 4K I2 minus I1 minus 1000 Ix, and since my Ix and I2 are in the same direction, you see, because no current is going to the 3 kilo ohms, so my I2 and Ix are the same, right? So I can call Ix to be equal to I2, right? So it's minus 1000 I2 plus I2 times 1K2 equal to 0. So once I get that, once I solve for this equation, I get I2 equal to minus I1. Since I know my I1, I know my I2 is going to be minus 4 milliamperes. Right. So now what's going to be my VThevenin? My VThevenin is just I2 times 1K, right? So that's just minus 4 milliamps times 1000, right? So that's like minus 4 volts. Okay. So now what this basically means is that if I assume my VThevenin circuit, now I can write this to be minus at the top terminal, and I call this as 4 volts, which is my VThevenin, right? Or I could do the same thing as write like this, plus in the positive upper terminal, I can call also minus 4 volts, right? So either is fine. All right. So now I know my VThevenin, which is minus 4 volts. Now I have to find out my RThevenin, right? So now for RThevenin, I turn off all my sources, independent sources. So that means since I have a current source, I'll turn it off. It will be an open circuit. So I'll write everything as it is. All right. Now, since I have a dependent source, right? Now I have to plug in a voltage source or a current source. In this case, I plug in a 1 volt voltage source, 1 volt voltage source across the terminal. Now I have to find out this current, Is. So once I know my Is, my RThevenin is gonna be just V by I, right? So that's like 1 by Is, right? That should give, this is 1 volt. That should give you my RThevenin. All right. So now I have to find Is. Now in order to find my Is, I could do is I could apply a nodal, right? Because I know the nodal voltage of this node, which is 1 volt, right? If I assume this to be a ground, now I can just assume this to be my one node, right? So now once I find my nodal voltage V1, my IS will just be 1 minus V1 by 3 kilo ohms, right? So now let's do for nodal voltages. Now I assume current going out from all the nodes. So it's like 1 current, 2 current, 3 currents. So I need 3 currents, right? So let's write the nodal equations. So therefore, my nodal equation is V1 minus 1000 Ix, right? Now what's my Ix? My Ix is V1 by 1K, right? It's V1 by 1K or 1000, right? V1 by 1000. So I can write my, it's V1 minus 1000 Ix, right? So instead of Ix, I can write V1 by 1000, right? Divided by 4K plus V1 by 1K plus V1 minus 1 divided by 3K is equal to 0, right? So once I simplify the equations, because I have only V1 in the equation, right? So once I simplify, you see this will just basically give me 0, right? This will just be 0 because this will cancel each other out, so this will just give me 0. So I will just end up having this part of the equation. So once I simplify this part of the equation, I get my V1 to be 0.25 volts. So now I plug this into the top equations to find my IS. So my IS is 1 minus 0.25 divided by 3K. So this basically gives me 0.25 milliamps, right? So what's my RThevenin? My RThevenin is 1 volt divided by 0.25 milliamps, which is just 4 kilo ohms, right? So therefore my Thevenin circuit would be 4 volt, 4 kilo ohms, like this. This is terminal AB, or you can replace this to be minus with a positive terminal at the top and negative at the bottom. Now you have to find out if a resistive load is connected between nodes A and B, what is the maximum power that can be transferred from this circuit, right? So your Thevenin circuit is just this one. If you connect resistance RL for maximum power transfer, you know that your RL has to be equal to R Thevenin or R Norton, right? So which has to be equal to 4 kilo ohms. Now, what is the maximum power that can be transferred? So therefore, if we have 4 kilo ohms in both the resistances, what's the voltage drop across this 4 kilo ohms across the RL? That's, since that's like half of the voltage source, right? So that's like 2 volts. So the voltage across this RL is 2 volts. So therefore, what's your P max? You could apply V square by RL, right? So since it's 2 volts, it's 2 square by 4000, which is basically equal to 1 milliwatt. So you can transfer 1 milliwatt of power across the RL. Now, this is question number 5. So you see a transient circuit here with an inductor and a capacitor. Now, at time 0, the switch moves to position B. So when it was at position A, from time minus infinite to 0, the capacitor was charged. When it moves to position B, the inductor starts charging, right? Because then only a current is flowing through the inductor. Before time 0, you see no current is flowing through the inductor because the circuit through the inductor is open, right? You see across the switch it's open, right? All right. So now we have to find out the voltage across the capacitor at T0 plus. That means just when the switch moves from A to B. So we know that the voltage across the capacitor cannot change immediately. So therefore the voltage just after the switch closes or moves from A to B is the same as the voltage at 0 seconds, right? So therefore we have to find out what's happening when the switch was at position A, right? So when the switch was at position A, you see the voltage will be fully charged. So the voltage, the capacitor will be fully charged. So therefore the capacitor will be open circuit, right? So if this is open circuit, no current is flowing, right? So the voltage drop across the 20 ohms is 0 volt. So what's the voltage across the capacitor? VC is the same as the voltage across the 80 ohms, which is the same as 40 volts, right? Because they are in parallel. So your VCT at 0 plus is 40 volts. Now you have to find out the equation for t greater than 0, right? For VCT. So now this 40 volts is the final capacitor voltage, right? This is the initial capacitor voltage. That was when the switch was at position A. Now if the switch moves to position B, so you see the capacitor will be start discharging through the 20 ohms and the 80 ohms, right? Because these 20 ohms and 80 ohms are in series, right? Because the capacitor now will be start discharging because this circuit is open. So this circuit is disconnected, right? This is 20 ohms, this is 80 ohms. So once it starts discharging, what will be the final voltage after infinite time? Your final voltage has to be 0 volt, right? So you know your initial voltage, you know your final voltage of the capacitor, you know your C, your capacitance is 1 microfarad, right? Microfarad. So what's your R Thevenin across the capacitor? Is just 20 ohms in series with 80 ohms, is 100 ohms. So what's your tau? The time constant is R Thevenin across the capacitor times C, which is just 100 times 1 microfarad, right? Which is just basically equal to 0.1 millisecond. And so since you know all the values, what's going to be your VCT for t greater than 0? It's VCT, it's going to be Vf plus Vi minus Vf e power minus t by tau, right? So that's just going to be 40. This is going to be 0 plus 40 minus 0 e power minus t by tau. So your VCT will be 40 e power minus 10,000 t volts. So that's your VCT for t greater than 0. Right. All right. Now for part C, you have to find out the inductor current at time t0 plus. That means when the switch just moves to position B. Now remember, the current through the inductor cannot change immediately. So initially, if the current at t is equal to 0 is 0 ampere, so this is the same current that has to be for t is equal to 0 plus through the inductor, because the circuit was not completed, right? Now once the circuit is completed, the inductor starts charging, right? And then there will be a current. But at t equal to infinite, you assume inductor to be a short circuit, right? Just like you assumed capacitor to be a open circuit. Now you have to find out the expression for IT for t greater than 0, right? IT is the current through this 16 ohms, right? Not through the inductor, but you could do that same way as we did for the capacitance, right? Because the transient phases now will be governed by the tau, which is because of inductor and the resistance across the inductor, R Thevenin, right? L by R in this case. Now we know our L, and what's my R Thevenin? R Thevenin is, I assume my voltage source to be short and my current source to be open, right? So this is my inductor. So you see, what's my R Thevenin is just 4 ohms plus 16 ohms, right? So that's like 20 ohms. So my R Thevenin is 20 ohms. So what's my tau in this case? My tau in this case is just 0.2 millisecond, right? You see, because the transient will be governed by the inductor in this case. The transient of IT, the transient across the current through the inductor, everything will be governed by this tau, right? So now for IT, what's my initial current, which is like uh, when the switch was at position A, right? So when the switch was at position A, there was no current through this branch, right? Through the inductor, because it was open basically across this 40 volts. So therefore my 5 ampere was going all through the 16 ohms, right? Since there was no current in this branch, my 5 ampere was going through the 16 ohms. So my initial current just before the switch was turned to B has to be 5 ampere, right? And the current direction matches, so it's positive. Now what's my final current? My final current is when my switch moves to position B, and at T infinite what happens? Now at T infinite you see the inductor becomes fully charged, so I assume this to be a short circuit, right? So I just ignore this one, I assume this to be a short circuit, right? So now right now you see you have a 40 volts, right? So for IF, so this is my II, right? So for IF, my circuit is gonna be something like this one, 40 volts. Right. Now you have to find out uh, this current, right? You have to find out this current I, right? So now I can apply mesh. So if I apply mesh, if I consider this to be I1, this to be my I2. So I know my I2 is equal to minus 5 ampere, right? So what's my loop 1 equation? It's minus 40 plus 4 I1 plus, since I'm considering loop 1, I1 has to be greater than all the other currents. So it's 16 I1 minus I2. So I plug my I2 in here. I simplify the equation. Then I get 20 I1 equal to minus 40. So my I1 is just minus 2 ampere. Right. So what's my I? If this is my I1 and this is my I2, right? This is my I1 and this is my I2. So what's my I? My I is just basically I1 minus I2, right? Which is just basically 3 amperes, right? So what's my IF? The final current is 3 amperes, right? So now I'll just plug in the equation, right? So that's like I final plus I initial minus I final e power minus t by tau, which is just basically 3 plus 5 minus 3 e power minus 5000 T. So this is just basically 3 plus 2 e power minus 5000 T amperes. So that's my IT. Now we move to the last part of the exam, which is the question number 6. So here you see this is a complex number problem. So here you see your Vs is given in cosine form with omega, right? So now remember, if the sources are given in sine, convert them into cosine, right? By 90-degree phase shift, and then proceed. Convert everything into the cosine format and then proceed. Now, the first part is like you have to redraw the circuit in frequency domain, clearly indicate the phasors Vs, Is, impedances, and R for RLC, right? Now, for phasor domain, you just have to write the amplitude and the angle. So your Vs in this case is gonna be Vs, right? Which is just gonna be V naught. So your Vs is just V naught, which is this amplitude. And what's the phase? Phase is phi naught, right? So that's your Vs. So I can just cut this time domain equation, right? What's my Is? My Is is gonna be like this. I don't know the angle yet, right? Since you have to ask, just read out the circuit. So I just cut this one. My resistance is gonna be resistance as it is. My C will be replaced by an impedance, which is equal to 1 by j omega C. This omega is the same as the source omega, right? This omega. So I take this L out, this C out, and my L is just gonna be j omega L. I'll just take this L out. So this is my phasor domain circuit. All right. Now you have to find out, so in part B, they have asked you to find out Z such that Z is purely real, and you have to show that that frequency, which is known as the resonance frequency, your omega naught is equal to 1 by root A, and you have to find out what is A, right? So now here you see that what's my Z, right? What's my Z? If I consider this circuit, what's my Z? If I call this Z equivalent, right? What's my Z equivalent? My Z equivalent is just resistance parallel with the capacitor, reactance parallel with the inductor reactance, right? So therefore my Z equivalent is just 1 by R plus 1 by j omega C plus 1 by j omega L, right? Now, if your Z has to be purely real, so that means this imaginary part has to be equal to 0, right? So now if your imaginary part has to be 0, that means your this one have to be 0, right? So therefore your j omega C has to be equal to just basically minus 1 by j omega L, right? So now if I take the j in the numerator, it becomes minus j, so minus minus becomes positive, right? So this becomes j omega L, so I can now cancel out the j's, right? So it becomes omega C is equal to 1 by omega L, right? So what's my omega? Omega is just 1 by CL. This is omega square, so omega is just 1 by root LC. So what's your A? Your A is LC. So this is the resonant condition, and the frequency at resonance is omega naught for this particular value. And for this particular value, your Z equivalent will be a real value. only resistances. The reactance of the capacitor and the inductor will cancel out, and this omega naught condition will only exist if there is an inductor with a positive reactance canceling out the capacitor reactance, which is negative. You cannot have omega naught for only capacitive system or only inductive system. Now for part C, you are asked to find out, to show that at resonance, which is omega naught, your currents in the capacitor and inductor are equal, and but are 180-degree phase shift. Right. So this is what you have to find. Now, what you could here you see that at resonance, that means you have to use omega naught equal to 1 by root LC. Right. You have to use 1 by root LC. Now, you see, what's the voltage across the capacitor? It's Vs. The voltage across the resistance, capacitor, and inductor is the same as the source voltage, right? Which is this one, because they are all in parallel. So what's the current through the capacitor? Let's say IC. It's the voltage, right? It's the voltage divided by ZC, right? Now what's my ZC? My ZC is 1 by J omega naught, right? Omega naught C. This is equal to what? J omega naught C V naught phi naught, right? So you see, instead of omega, I'm writing omega naught because they have asked like at resonance what's happening. Now, what does this J is doing? This J is, if you multiply a number by J, that means you are just adding a 90-degree phase shift, right? So this basically means omega naught C V naught phi naught plus 90 degree, right? So that's my IC. This is my IC. Now what's my IL? My IL is the same voltage because it's in parallel divided by ZL, right? So now what's my ZL? Is J omega L, right? So since the J is at the bottom, if I bring it at the top, it becomes minus J V naught by omega L times phi naught, right? So this basically means V naught by omega naught L, and because of this J, if I move it inside, I will have a 90-degree phase shift as before, right? So I'm gonna have 90-degree phase shift. Now because of this minus, I will have 180-degree phase shift also. So now you see your IL has a phase shift of 180 degree greater than IC. Now that we have shown that IC and IL are 180 degree phase shift apart, we have also have to show that they are equal, right? Because you have to show that they are also equal. Remember, two conditions equal and 180 degree phase shift. So we have shown 180 degree phase shift. Now we have to show that they are equal at resonance. So now let's write IC again, which is just omega naught C V naught with an angle of phi naught plus 90 degree, right? Now, if we plug in omega naught, right, at resonance, which is just basically 1 by root LC, if we plug in this value, so we get an IC value of 1 by root LC times C V naught phase of phi naught plus 90 degree, right? So we see we get root C by L V naught phi naught plus 90 degree. So that's for IC. Now for IL, we got V naught by omega naught L. Angle is phi naught plus 90 degree plus 180 degree, right? So similarly, if we put omega naught here, we see that we get magnitude or amplitude of V naught root LC by L, right? Angle of phi naught plus 90 degree plus 180 degrees. So you see we get also for inductor C by L V naught. Phi naught plus 90 degree plus 180. So you also see that for IL, the amplitude is same as IC, so they are equal. That's the first condition that they're asking you to prove, and the second condition is the phase are 180 degree apart. So you see also the phase are also 180 degree apart.